Hello and welcome to this PIR Live Event webinar, brought to you in part by Partners in Research Canada. My name is Ben Hobbs, and I will be your host today. I would like to introduce our guest today, Dr. Christine Wilson, a distinguished university professor in the Department of Physics and Astronomy at McMaster University. Thanks for joining us, Dr. Wilson. I will let you take it from here.
All right, thank you. Okay, perfect. So what I'm going to talk to you about today for a few minutes is some of the research that I do and that other astronomers do around the world using a very new telescope, which is called the Atacama Large Millimeter Array. And the title of my talk is New Eyes on the Cold Universe, and you'll see why that is in just a moment. So my research in astronomy focuses on very long wavelength observations in the radio and the far infrared. And so this isn't a wavelength range that people typically think about very much. And so I just want to give you a little motivation for why astronomers care about what I call the invisible universe. And for me, the invisible universe is looking at any wavelengths in the electromagnetic spectrum that are not visible light. So as you can see from this graphic here, visible light that we see with our eyes is a very small range of wavelengths from about 400 nanometers in the blue and the violet to about 700 nanometers in the red. But objects in the universe produce radiation at a very wide range of wavelengths. And the wavelength range where they produce most of their emission to first order depends on the temperature of the objects. So that objects that are very, very hot will actually produce most of their energy at short wavelengths in the ultraviolet or even X-rays. And so, for example, a star that is 50 times more massive than our sun will be visible in the visible light that we see, but most of the energy will come out at these short wavelengths. And then very cold objects emit all of their energy at the long wavelengths, in infrared wavelengths or microwave or even radio wavelengths. So astronomers around the world use a very wide range of telescopes, both on the ground and in space, to probe the full range of the electromagnetic spectrum. Because if we just limited ourselves to visible light, we would miss large parts of the universe, large parts that I think are very important. So just for a visual illustration of this, this is a wide angle view in visible light of a constellation that might be familiar to you if you've ever looked up at the sky. I think after the Big Dipper, the constellation Orion is probably the best known constellation for people living in the Northern Hemisphere. It's visible in the wintertime, so that if you went out this evening, if it was lucky enough to be clear, you could probably see Orion. And it's familiar because of the bright stars and the three stars close together that form Orion's belt. This is Orion the Hunter. If you look at the same patch of sky at far infrared wavelengths, so this is at a wavelength of 60 microns, this is what Orion looks like. And if you didn't have those green symbols there showing you where the stars were, you would be hard pressed to know that you were looking at the same region of the sky. So at 60 microns, what we see in Orion is not the stars that have formed there, but the clouds of gas and dust that are still in the process of forming new stars even today. So I want to say a little bit about ALMA because it's a very exciting new telescope that came into operation, just began operating in 2012. So it's been operating for less than 10 years. So ALMA is a big radio telescope built in a site in northern Chile at an elevation of 5,000 meters. It's the first truly world telescope. It's a global partnership involving countries in North America, Europe, and East Asia, and of course our host partners, Chile and South America. ALMA is a radio telescope, and it has a total of 66 antennas, and you see some pictures of them here. The main powerful array of ALMA is a set of 50 telescopes that are each 12 meters across. And then there are 4 additional 12-meter telescopes that are used to see, and a very compact array of somewhat smaller telescopes. And these telescopes are all used together, essentially producing what is a much larger telescope. So with ALMA, we can make images that are as sharp and crisp as you could get if you could build a single telescope that was 12 kilometers across. Now, we can't build a telescope that big. That's just kind of silly. But by linking these telescopes together and spreading them out across the surface of the desert, out to distances of 12 kilometers, we regain that very sharp image that we need to study fine details of forming stars and forming planets and forming galaxies even in the distant universe. So one of the most iconic images from ALMA is this image of a disk of gas and dust around a young star in the constellation Taurus, which is not very far from Orion on the sky. And this particular object is known as HL Tau. This was our first image with ALMA that really showed fine details in a disk of gas and dust that is in the process of forming planets. And these rings that you see in the image here are produced by the effects of the motion and the gravity of the planets forming in the disk. We can't see the planets themselves, but we can see these rings. And the sharpness, the resolution of this image at the 450 light years of this star is 5 astronomical units. And so that means we have about the resolution in our own solar system equivalent to the distance from the sun to Jupiter. So 1 astronomical unit is how far away from the sun the Earth is. So it may not seem like really great resolution when you think about it in terms of our own solar system, but it's a really fantastic achievement. And this sharpness of this image is better than any optical telescope that we operate today, including the iconic Hubble Space Telescope. So this press release came out over 4 years ago, and just last December, a new major campaign with ALMA produced images of about 20 of these nearby disks around young stars that are forming planets, and a montage of them is shown here. And you can see the fantastically complicated structures in these images and how prevalent these rings structures are around young stars. So we're learning so much about how and where planets form in nearby stars using ALMA. Now, my own research focuses on the formation of stars, but in very different systems. I'm interested in how stars form inside entire galaxies. And one of the objects that I have studied quite a bit is this object, which is known as ARP-220. It is a galaxy that is about 250 million light years away, but it is the closest example of its class of galaxies. It's a galaxy that emits most of its radiation, more than 95% in the infrared wavelengths. And the amount of energy that is produced in this galaxy is really just phenomenal. If we look at the rate at which this galaxy is forming stars, it is forming stars at a rate that is 200 times faster than the rate in our own Milky Way galaxy. And it's doing that formation of stars in a very small volume of space, a volume of space that is 1,000 times smaller than the volume of space forming stars in the Milky Way. So that gives you an intensity of the star formation process that's 100,000 times higher than in the Milky Way. So this is just a phenomenal object. So working with collaborators around the world, in the United States and in Europe, we made images of ARP-220 with ALMA, looking at the emission from the dust, which is the figure that you see in the left here, labeled continuum, and images from the gas directly, which is the image on the right. And in both cases, we see these two bright concentrated regions. ARP-220 is an example of a galaxy where two spiral galaxies like the Milky Way collided and merged. And they're not quite finished merging yet. Those two bright spots that you see are the centers of the two original galaxies that formed. And so we're looking at this galaxy with a resolution of about 1,000 light years, which lets us measure some of the detailed properties in the two nuclei. And one of the outstanding questions about ARP-220 that we still don't know the answer to is whether either of these two nuclei contains a massive black hole. Many galaxies do have massive black holes, so this galaxy likely does, but there is so much gas and dust in this galaxy that even X-rays can't escape from around the regions around the black hole. And so we are still sort of searching to understand what so that's all I wanted to say today. ALMA is this revolutionary instrument.
Christine, I'll just stop you there for a moment. I think we're getting some feedback from your headset there. Is it possible to just use the speaker in your computer?
I will. Is it better now?
Yeah, it's much better now. Thank you.
Sorry. It's probably when I talk with my hands and I was probably bumping the cord. I'm sorry.
Okay, no problem.
Do you need me to go back?
Maybe just repeat that last slide. I think we missed that one.
Okay, I'm sorry. So the question we have about ARP-220 is, one of the questions is whether there are massive black holes in the centers of either of these two galaxies that merged to form ARP-220. And the difficulty is that we can't see the radiation from the disk of material around the black holes because there's so much dust in the way. It's like looking through a smoke screen or a fire. It obscures our view. And so we have to use indirect methods to try to figure out if there are massive black holes in either of these two galaxies, and that work is still ongoing. So that was the last thing I said about this galaxy. So ALMA is a fascinating new telescope. It's incredibly powerful. It's only been in full operation for about 6 years, and there's just all kinds of exciting new results coming out from ALMA. And I look forward to trying to answer any questions that you might have.
Well, thank you. So to get started today, you mentioned that hotter objects often emit shorter wavelengths of light. Why is that?
So one of the simplest way to think about it is that you can think about any object in the universe, including us, is radiating heat, right? Any object has some temperature, and the energy being radiated from an object at a certain temperature is known as black body radiation. It has a characteristic shape of brightness as a function of wavelength, and the peak of the emission depends on how, the wavelength of the peak emission depends on how hot the object is. And so, for example, we produce most of our emission in the near infrared wavelengths of a few microns. That's why night vision goggles work so well, is that they're tuned to look at infrared radiation. And so an object, the surface of our sun is about 5,000 degrees. A star that was 30,000 degrees would emit most of its radiation at shorter wavelengths. And so to first order, it's just a question of how warm or cold the objects are. The gas and dust that I study is typically a few tens of degrees above absolute zero. So that makes it something like below -200 Celsius. And so that's why it produces very long wavelengths.
So if astronomers are using radio waves to view an object, are they essentially listening to that object then?
Not really. I mean, so listening to an object is you might think of the iconic movie Contact with Jodie Foster and her headphones. What we are measuring is essentially a radiostatic hiss, but it's not being really measured by listening. It's like any other detector in at different wavelengths. We're essentially capturing the photons. So you may have heard light referred to as being photons of light. radio waves, radio emission is also photons. They are just lower energy photons. So what we're trying to do is capture as many of those photons as we can to build up the information about the image.
Okay, so our next question today comes from Mr. Sambala's classroom, and they're wondering, when you look at those images of newly born stars surrounded by a gas ring, can you tell what the planets are made from? Are they gases? Are they solids? Can you tell what elements are in them?
So that's a really good question. We can't tell what elements are in the planets from images like that. But what we are beginning to be able to do is to understand something about how far away from the star the planets are, and some understanding of how much matter the planets have, how massive they are. And astronomers are doing this by comparing the detailed structure of those images to computer simulations, where they simulate a disk of gas and dust around a star, and then they put a planet in at a certain radius and watch to see how the gravity of that planet affects the structure of the disk. And so by running many models and comparing them to the images, you can understand, for example, is the image likely have a planet like Jupiter, or is it a planet 10 times as massive as Jupiter, or maybe it's a somewhat smaller planet like Neptune? So we're starting to be able to do that, and having larger samples with better statistics is important for that process.
So is the mass of a planet an indication of what that planet is made of?
Yes, the mass of a planet relates to what it's made of. So very massive planets like Jupiter will have a lot of their mass in gas, and a lot of their mass will be hydrogen and helium, because most of the universe is made up of hydrogen and helium. Things like carbon and oxygen that we're made of are less than 1 part in 10,000 of the total amount of material in the universe. So for a planet to be very massive, it pretty much has to start collecting that hydrogen and helium to build up its mass. The lower mass planets, when they get down to being maybe a few times the mass of our Earth, those are almost certainly composed of normal solids or maybe solid ices, because they're not massive enough for their gravity to let them hold on to the hydrogen and helium. And then the in-between mass planets like Neptune may have some amount of the gases, but also a lot of ice and rock and so on.
So our next question today comes from Miss Amiote's classroom, and they are wondering, what is the furthest object we can see?
The furthest objects we can see, I apologize for that phone, I can't really easily stop it. The furthest objects we can see are very young galaxies out in the distant universe. And at those large distances, astronomers talk about redshift. So the redshift of the objects is about 8 or 9. I'm not a cosmologist, so I don't hold those distance scales in my head, but we certainly can see objects far enough away that the light has had to travel at least 10 or 12 billion light years to get to us. So we can see objects back to when the universe was very young, within 1 billion years of the Big Bang is how far out we can see.
Interesting. So do galaxies orbit other galaxies, and is our galaxy orbiting a particular object?
So that's a great question. So galaxies can orbit other galaxies. Our galaxy is not orbiting any particular object, but our galaxy is in a small group of galaxies that we call the local group. And there's one other big galaxy in our group, which is the Andromeda galaxy. And so our galaxy and Andromeda are a pair of galaxies that are orbiting around each other. So you don't say that one's orbit, they're both doing this sort of dance around the center point between them. And then there are smaller galaxies in our local group, and some of them are orbiting our own galaxy. There are a couple of galaxies you can see in the southern hemisphere called the Magellanic Clouds that are orbiting our own galaxy. And many galaxies in the universe are in small groups like the local group, and then there are some galaxies that are in very big groups, or even things we call clusters of galaxies, where all the galaxies are orbiting, are sort of moving randomly around in the total mass. They're feeling the total gravity of that entire system, and then they're orbiting around in that system.
So Ms. Reynolds' classroom is wondering, they want to know your thoughts on the probability of life on exoplanets.
So this is another really great question. So my feeling is, we know there are so many stars in our galaxy, and then there are billions of other galaxies. And we know now from looking for planets that a lot of those stars have some planets. So I bet there is life of some kind on some other planet. What I don't know is if we will ever know that for sure. I don't know if we'll ever be able to find direct evidence for life. People are working very hard, and they're planning future missions to try to look for evidence of life on planets that we can see. That, whether we will ever know for sure, that is a harder question to say. But I have to believe that somewhere else in the universe there is life. Whether we would recognize it as life is another question. Whether it's more than bacteria, we don't know. But it's hard to imagine that our planet is the only one that has any kind of life.
So why is it that galaxies merge together?
So galaxies will merge together if they happen to come close enough to each other, and if they're not moving too fast. So coming back to the local group, people can take can model the orbits of our galaxy and Andromeda, so we know how far apart they are and what direction they're moving, and we know how massive they are. And we can model those orbits into the future. And what we predict is that, in fact, the Milky Way and Andromeda will merge together, and I think the prediction is in about 5 or 7 billion years. So essentially, because many galaxies live in small groups, they have a reasonable chance of merging at some point. In the universe today, if we look out and we sample many thousands or tens of thousands of galaxies, a very small fraction of them will be merging when we look at them. But over time, mergers are quite significant.
Would it be fair to say that our own Milky Way galaxy is the product of smaller galaxies that have merged together over these large timescales?
That is certainly a process that has happened and is still happening. So we can see the effect of small galaxies being torn apart when we look at the stellar properties of our galaxy. And with some big new survey missions like Gaia, people are starting to find evidence for older mergers, old streams of stars in the Milky Way. What I'm not sure about is whether our galaxy was built up completely by taking lots and lots of little galaxies and merging them together, or whether there were a few bigger ones that merged, or whether there was a big center that kind of formed as a structure and then accreted a lot of little galaxies.
So you mentioned earlier that the ALMA telescope is an international collaboration between multiple countries. Why is this done as an international collaboration, number one? And number two, is this standard practice for these large telescope projects?
So part of the reason a big telescope like ALMA is an international collaboration is due to cost. I didn't say it specifically, but I had it on my slide that the telescope cost about 1.3 billion US dollars. So that's quite a lot of money. It's less than the cost of a commercial jetliner, but it is a lot of money for science. And so that's part of the reason that the different countries came together to build it. I was involved in the planning for ALMA for a long time, more than 20 years. And at one point in the late 90s, there were 3 separate proposals to build arrays like ALMA in Chile, one from Japan, one from the US, and one from Europe. And then over a period of a few years, they merged their efforts because what they realized was they could build a more powerful telescope if they all got together. It's also a big job to build such a big telescope. You need a lot of the people power around the world to be working on building the components and so on for the telescope.
And why is, oh, sorry, I'll let you finish there.
I was going to say the second part of the question about international collaboration. Yes, this is very common. ALMA is the first one that is such a multinational organization, but Canada is involved in several big telescopes, and in all cases we have partners. So our first international partnership was the Canada-France-Hawaii telescope, which was built in around 1980, and that was a partnership between Canada and France and the state of Hawaii.
So why is it that the ALMA telescope is a collection of smaller ones instead of one big telescope?
So part of it is that so first of all, if you wanted to build a 10-kilometer diameter telescope, that's an awful lot of steel, just thinking about that, and let alone anything else you need to build the telescope. Another thing is that you want to be able to pick what direction in the sky you're looking. And so you can think of, with a radio telescope, it's kind of like a satellite dish for your television or whatever. You can steer the telescope, you can turn it, you can point it to the east, you can point it straight up, you can point it to the west. And so you can pick out which object in the sky you're looking at. With a really large telescope, 12 kilometers across, you wouldn't be able to steer it. It would have to be fixed on the ground. And so you'd have to wait for the sky to drift past where your telescope looked. So there are a lot of reasons why also a very big telescope like that would only be able to look at one tiny part of the sky at any given time. And that would make it harder to observe.
Do you think it's more valuable to invest resources into telescopes or into spacecraft, and why?
So they're very complementary. We really need both. So the reason that space telescopes are much more expensive in general because they have to be launched into space. That's expensive. They need lots of computing power and people power to operate them, and they tend to have short lifetimes as well, and you generally can't go up and fix them if something breaks. The Hubble Space Telescope is a notable counterexample, but we need the space telescopes because the Earth's atmosphere blocks our view of a lot of the electromagnetic spectrum. So we can see in the radio, and that's why ALMA and other radio telescopes can be built on the surface of the ground. We can see in the optical, but we cannot see in the infrared. We can't see in the ultraviolet. We can't see in the X-ray. The water vapor in the Earth's atmosphere makes the atmosphere opaque. It's like looking through fog. So we need those space telescopes to be able to look at the full range of the electromagnetic spectrum. So they're very complementary.
Can this new ALMA telescope give us, and I may be pronouncing this wrong, but give us information on what might be in the Bootes void?
The Bootes void. I'm not familiar with that. Whoever's heard of that, is that a galaxy structure, or is it in our own Milky Way?
I'll wait to see if I get a response. It was from Ms. Riddle's classroom, spelled B-O-O-T-E-S.
Yeah, Bootes, it's a constellation, yeah. Okay, so I think, thinking about my knowledge of the sky, which is a bit rusty, so I think the Bootes void is a region of space where there are not very many galaxies. If I'm wrong, then there certainly are regions like that in space, so we'll take that and go on with it. So I think, probably ALMA isn't the telescope to try to figure out what's going on or what's in the Bootes void. ALMA is a great telescope. It's not particularly good at surveying large areas of the sky rapidly. For that, our optical telescopes are generally still the best, because I think partly because we're very visual creatures. We use our eyes a lot. Our technical capabilities for optical detectors are much better than most of our radio ones. And so people are building big optical cameras that can look at more than the area of the moon at once. And that's what if I were trying to figure out, was there anything in the Bootes void and what was there and what was it doing, I would start in the optical.
Okay, and I think you have it right, because she's confirmed it's a supermassive void where there is little matter.
Okay.
So we're running out of time today, but just before we end, I was hoping to have you speak a little bit about your career path and maybe some advice you have for students that are watching today that are considering something similar.
Okay, so I was thinking, so one of the things I wanted to pass on was that I didn't know when I was in school that I wanted to be an astronomer. I didn't even know that I was interested in physics particularly. So when I graduated from high school and went to university, I was at the University of Toronto. I was in the Faculty of Arts and Science, and I didn't know what I was going to major in. And so I took a lot of different courses in my first year. And I only really committed to studying physics and astronomy at the end of my second year. So I took courses, I really enjoyed them. I loved my astronomy course. Physics was hard, but challenging and interesting. And so essentially that's how I started down the path towards physics and astronomy. So my advice as a student to you is to keep your options open until you find something that you're interested in, that fascinates you, that you enjoy, because it's going to be a lot more fun when you get out into the workforce if what you're doing is something that you enjoy. And whether that is computer programming, whether that is mixing things in test tubes in chemistry. It's a long time since I did chemistry. Maybe you really like, getting out in the woods and learning about, plants and animals, ecology. Find something that you're really interested in and follow that, because generally speaking, you will be most successful in the long run if you're doing something you're interested in. That's my philosophy.
Well, that's all the time we have for today, but thank you, Dr. Wilson, for taking the time to share your research with us and for answering all of our questions today.
Thank you.
Next week on PIR Live Event, we will be discussing global food security and farming for a sustainable future with Dr. Navin Ramankutty from the University of British Columbia. More information about these webinars and other PIR educational programs are available at pirweb.org. Thanks for tuning in and have a wonderful day.